Q. Okay. Okay, let me quickly explain, a little bit about linear regression. Okay, linear regression also helps us to do regression on nonlinear models as well. So if you learn linear regression properly, you can use the same information to do regression on nonlinear models. Let's assume we have a graph, right? I'm straight, you can see my graph, right? So let's take an exponential curve. It's a nonlinear curve, right? Say, this is an exponential curve. It's e to the power x. That's a nonlinear curve. Now, what about a logarithmic curve? That's log x, right? That's a nonlinear curve as well. Now, a linear curve y is equal to x is right here. Okay, y is equal to x. This is a linear. You can do regression. If you do, you can do linear regression on this. But to do regression on this, say exponential curve or a logarithmic curve, what you can do is, if you take a logarithmic of an exponential curve, what do you get? Anybody? If you take a logarithmic of e to the power x, if you do a log of e to the power of x, what do you get? You get this line. Okay, so log of e to the power of x is equal to x log e. This cancels out, you're left with x. So y is equal to, so you get this, you get a linear line. Now what about log x? If you take an exponent of log x, what happens is, again, this will get canceled out and you get x. So that's, and there are other transformations you can do, other linear transformations you can do, but this is what it is. You do a transformation of a nonlinear function to a linear function, and then you can do linear regression. So is that clear? Is that clear? Does that make sense? Okay, now let me quickly explain what is the basics of how is linear regression done here. Okay, let me see if I can quickly, I need to erase these guys here. All right, let's talk about how do you go about doing linear regression. Okay, what is linear regression, right? Let's say you are given a set of points, right? And we are given, say, there are some random points. Let me take this here. It's kind of messy. Okay. Let's say you're given a set of points here. Okay. And our job is to find, we need to fit a line here. Just based on looking at this, we can say that if you do a linear regression, we would find a line going like this. The slope of the line would be somewhere close to about 1, right? So how do you go about it? So what they do is, initially you go and you fit a line, means you just you put a horizontal line, okay? And this is the mean of the y values. So if you project these, take just the y values, what will happen is you get these points here, right? We get the corresponding points here, and we find the mean of these values. Say the mean is somewhere here. Now what you do is you take the differences between these 2 points with these means, and what you do is you square them up. So how would you? It's more like, yeah, you just square the differences and you take a sum of that. It's called, what is it? It's called when you take the sum of these squares, it's called the variance of the mean. So it's called as the variance of the mean. Okay. Now, with this information, now what they do is, like usually they use a computer for doing this, but now for these points that you have here, right? Let's see, I'll now try to erase these lines here. This is definitely a lot messier than I thought it would be, but okay. So we have these points, okay? Now what they do is they start off with this particular line, and then they slowly start And then they calculate this variance of that mean, whatever variance of that particular line, and they keep doing that. They keep turning the line like this till vertical, like like they start horizontal and then slowly they keep turning the line. And for every line they do, what they do is they try to go and plot this variance of the mean in another graph here. So they'll start off with a particular, like with the horizontal line, and then they go till vertical, right? So as they are going, they plot this, so they will get a curve like this. What will happen is this variance of that, whatever curve that we take, it will form at some point, there will be a variance of that fit that will be minimal. This is the minimum when compared to the other ones. So you start off with this, and then you slowly start turning, and then here is this one, and then this like this. So these are various slopes, and what they do is, again, they use, if you are trying to find the minimum of a curve, that's a calculus problem. You differentiate it and try to see like for which point you get 0, and then they will pick this one. They pick this particular curve, right? And then they draw that. So now you have a fit that has the variance, or these are called residuals, right? So the difference between this one and this residual is the sum of the squares of the residuals is the minimum when compared to various other slopes that we pick. So this is the best fit. Now this is called, so this is the variance. And so if you take the sum of these residuals and of your sum of the square of the residuals, you get the variance of the fit. Okay. And this is guaranteed to be a minimum if it is for a good fit. Now there is another term here. It's called the R. I wish I can use a different color here, but okay, there is. So how good is this fit when compared to this variance of the mean? When it was horizontal line, it's probably the worst. So there is a formula. Again, I'm trying to use a different, let me use this itself. So variance of the mean minus the variance of the fit, okay, divided by the variance of the mean gives this is called as R square. So what this R square means is, like, given, say if you compute the R square of various other things, you will see that for the perfect fit, this R square is the highest. And again, when you do a linear regression model, you can quickly see that what is the R square, and if the R square is closer, this can never be, it ranges from 0 to 1, okay? So I would say, yeah, I mean, like, yeah, you can say there, it's an opening. So yeah, it's like 0 to 1. It's never going to be negative, but the more closer it is to 1, say it's like you get something called 0.89, or like, yeah, like, no, 0.89, let's say 0.89. That means this is the fit is pretty good. If it is say 0.60, it's like, it's not that very good. But it's, again, so this is, and again, because it's a straight line, y is equal to the alpha plus beta x or something. So again, this is the alpha, this is the y-intercept, and the slope is the beta. So this is the slope. So, and again, what happens is, because one more thing is these residuals, this is also called the errors, right? So the residuals, they form a normal distribution. If you take these residuals and you plot it, let me use the same graph here. So if you plot just the residuals, the errors from this particular line that we found, if you take this difference and you plot it, you will get a normal distribution. So these are the residuals. And then what you do is, so this is an indicator, this slope is an indication that's the coefficient of this particular line. but and again, we cannot, because of these what do you call residuals, right? The residuals, and they form a normal distribution. This, okay, mathematically we found this line to be this, but in reality, a point will be somewhere like this. You know, it could be, it's not exactly on the line, but it will be somewhere. And we can predict the range in which you can find the next point. That is usually within it follows, like say, if we find the mean of this, whatever x that we find, right? So it's not an exact point that we can say, but we can say that it's within the range, right? What is the range? Usually they say like within 95% confidence interval. And there are some formulas to go about it, but for now I'll stop it at that point. You can say that yes, it is going to be, say, given a particular value of x, we can figure out the actual y based on this regression line, and then you say that within an interval of with 95% confidence that it ranges between this and this. So, and then we can add a plus or minus to that particular y, and there you go. That's how you do linear regression. Again, like I said in the beginning, if you have a nonlinear equation, you can transform that to a linear equation, and then you can do a linear regression on it. That is linear regression in a few minutes. Now I will